good afternoon or good morning to everyone joining in for the beginning of our three-hour sessions on the analysis of the 2017-2021 American Community Survey with R and Tidycensus. This is, as I said, three different three-hour sessions over the next 3 Wednesdays. Today, the 8th, the 15th, and the 21st, each with 3 different topics. Today we're going to be working with the American Community Survey using R and Tidycensus. Next week, we're going to be looking at mapping and spatial analysis with the ACS using R. And then 2 weeks from today, we're going to be looking at working with geographic data and making maps with Python. This is a new program that we're introducing into our series that we haven't done before. And we are so privileged to have doing these presentations Professor Kyle Walker of Texas Christian University, professor of geography there, and also director of their Urban Studies Center. But more important, he is a top analyst in using R and related projects that he's helped to produce specifically for analyzing census and American Community Survey data. He's just the main guy to do this stuff, and we're so pleased to have him part of our project. Each of these surveys, each of these 3-hour sessions are going to be self-contained, and they also don't require you to have a great deal of knowledge about using R or the other products that we're looking at here. It's something that it's an unusual situation that we're able to do this right after the 5-year data from the American Community Survey, that is the 2017 to 2021 American Community Survey, just came out in the last few months. And you're going to be able to learn how to use this with these new fantastic programs. This series is being sponsored by the Social Science Data Analysis Network, which I direct. I'm William Fry. And at the University of Michigan, over the last several decades, we've been trying to find ways to make census data accessible to teachers and students, even in courses that never had data analysis before. So we go the whole spectrum, from new users, new students, freshmen and broad sociology classes or economics classes or other disciplines, to try to integrate some census data into their analysis, into their studies, up to graduate students. And of course, many people learning to use R are going to be in that boat. So our mission is to try to make census data accessible to a broad spectrum of people, especially teachers and students. But of course, we're open to having other people as well, researchers as well. As I say, we're located at the University of Michigan, and we do several webinars. We have a website, ssdan.net. The Social Science Data Analysis Network. But I think that's enough of an introduction. I think we're going to go right to Kyle. Kyle tells me that today being shipped is his book, Analyzing U.S. Census Data, Methods, Maps, and Models in R. So you're going to get a fresh approach from this new book and probably have a chance to buy it very quickly if you want to. But you just can sit back and work with Kyle today and learn all there is to know about the American Community Survey and how to analyze it in R. So take it away, Kyle.
Well, thank you so much, Bill, for the kind introduction. And wow, thanks to everyone who's come out. Looks like we have over 250 people in attendance today, which is over twice as many as we've had in past years. So I am so appreciative that you have taken some time out of your busy schedules to hear me introduce some of these tools and share some of the work that I've been doing with you. And hopefully you'll get some kind of interesting value add out of it. So we went through the introductions. And so we start flipping this through just to kind of reiterate, a little bit about me. I wear a bunch of hats professionally. I'm an associate professor and I'm chair of the Department of Geography at TCU. I've been at TCU over a decade. I work broadly as a spatial data science consultant as well across a number of different industries. And I have had, I think, as a result of that, a really interesting opportunity to see how census data are applied across a wide variety of areas, whether it is in industry, thinking about real estate, healthcare, or on the education side of things, in scholarly research and industry research. There's so many application areas for this information. And I've really tried to kind of put out materials, this included, with that in mind. So regardless of what discipline you're coming from or what field of practice you're coming from, hopefully there'll be something in here across these different workshop sessions for you. So I kind of, originally I did not specialize in data science when I was coming through grad school, but have really found that to be my passion with regards to the work I'm doing now. So I've developed a number of R packages, some of which you'll get to know over the course of these workshops. Tidycensus is the main package that you will be learning about today. And Bill mentioned my book, which is just coming out right now. So technically the release date is February 16th. I have gotten some pings of people receiving hard copies in the mail as early as today. I still don't have a hard copy myself, but I'm very excited to see that in print. If you're interested in any of the information that is presented in today's presentation, that book expands upon everything. So you can buy from Amazon, or you can buy directly from the publisher on from CRC Press. If you find this information useful and you're really thinking about, well, how can I, support these projects, going and grabbing a hard copy of the book, buying a hard copy of the book, I would really, really appreciate that. So please do check that out, and I hope you like it. So let's start digging in a little bit. Bill gave an overview of the workshop series. I'm going to delve in a little bit more if you're thinking about structuring your attendance over the next couple weeks. So today is all about getting up and running with R and Tidycensus. I'm not assuming any prior knowledge or experience with R here. We're not going to do a full-fledged introduction to R. We are going to dive right in, but it will be an introduction to Tidycensus. But even if you've used Tidycensus before and related tools, you will still maybe find some new things or new application areas in today's program that you might not have used before. Next week, we're going to cover mapping and spatial analysis with ACS data in R. I'm excited about this one. Mapping is typically, one of the most popular, it's certainly the most, popular chapter that comes up in my book. And people are always asking me about how to make maps with census data. So we're going to learn all about map making and working with cartographic visualization of census data next week, specific to the ACS, but you'll also learn some analytical tools for analyzing topics such as segregation and diversity and thinking about business analytics applications. I'm excited for that one. And then February 22nd, branching out a little bit. Our previous workshops, we focused on R, but I have dipped my toes into Python development in the past year and released in late 2022 a brand new package called Tigris, which is a port of my Tigris package to Python. It allows you to work with US Census Bureau geographic data sets in Python. And so if you're interested, if you have used Python before, if you've never used it, come check it out. We're going to be going over how to work with geographic data, make some maps in Python, and access census data. All right, so today's agenda, just so we were kind of thinking about how we're going to handle things over the course of today's talk. It's a 3-hour program, but that program is organized into 3 blocks. The first block is going to be an introduction to the ACS and Tidycensus. So, what is the American Community Survey? What is the 2021 American Community Survey, the new data that just came out? And how do you access that data with Tidycensus? So we'll walk through that. Hour 2 then will focus on analysis and visualization. And these are massive topics, so we can only scratch the surface, but I'm going to show you some analytical tools with the popular tidyverse framework in R for analyzing data that you get back using Tidycensus. And then we're going to walk through a visualization workflow. How do you start with data that you've acquired with Tidycensus from the ACS and step through a visualization process to actually make a chart intuitive? Because, it's one thing just to say, here I have data, I'd like to make a chart, but rarely are those charts all that great at the beginning. And so what I'm going to be stepping you through is kind of my thoughts around chart design, and we'll go from a relatively unintelligible plot to something that's a little bit more workable. And in hour 3, if you've never worked with microdata in the ACS before, stick around for that. ACS microdata, the public use microdata series, or PUMS data, are fascinating and potentially underutilized data sets outside of the academic social sciences, where you can actually get access to individual level anonymized records from the ACS. And that allows you to create custom tabulations that aren't available in published tables. And I'm going to show you how to use that. And we're going to create some of those tabulations and learn how to work with those using tools in Tidycensus. So I'm excited for that. What we're going to do, and I'll be keeping an eye on the time as well, I'll go about 50 minutes per hour with content. So I'll go up until about 1:50 Eastern time with this first hour. We will break for 10 minutes until 2 Eastern. And that is a great time to do some exercises that I'll leave up on the screen, ask some questions. I have the Q&A up. And we're going to do our best to kind of answer as many questions as we can. One caveat is the questions that we will tend to answer are going to be more thematic in focus, just with the volume of participants. Debugging kind of errors or technical questions ends up being something that's pretty difficult. So, that's just something to keep in mind. Even if there are, if there are issues that arise, these are things that, hopefully if there are broad issues, we can address that. But just kind of keep that in mind as we proceed. And so moving forward, we're going to jump into working with the ACS. I want to spend just 1 minute going over how to get booted up with the workshop. As we were discussing beforehand, there are probably kind of 3 groups of participants in this workshop. And I think we have a format that is going to be accessible to all 3 of those groups. So watch your chat right now. I'm going to send a message right now into the chat. It has 2 links. One is a link to the GitHub repository for these workshops. Excuse me. That has all sorts of materials. I'm going to jump over there in just a moment. The second link links to Posit, formerly RStudio Cloud, which is a cloud environment, a pre-built cloud environment that allows you to run the code in these workshops. So let me jump over real quick to that GitHub repository and talk to you about how this works. So if you follow the GitHub link that I just posted, you're going to see, if you've never used GitHub before, maybe something that looks a little unfamiliar. So I'll step you through what we're looking at here. These are folders that contain various files that we're using. You don't necessarily need to worry about that unless you're an advanced user. If you want access to the slides that I'm showing you right now, this link here will take you to those slides and you can follow along. You can copy paste the code out of the slides. There are also going to be a number of embedded links in the slides that you can use. So I mentioned there are probably 3 buckets of participants, broadly speaking. First, some of you will be existing Tidycensus and R users. So you know about RStudio and R, you know about Tidycensus. You've been using these in your own jobs or projects for some time. For you, you might have some more comfort with GitHub and you might be running a local version of R and RStudio. And so what you can do, so long as you have Git set up, is you can clone this repository to your computer, and that will pull down all of the code and materials that you need to run the workshop. Alternatively, if you don't want to use Git, you can click on this ACS 2021 folder, click on the ACS 2021 code.r file, and you can either download this file or frankly, you can just copy paste from here. So alternatively, so that's one bucket. Another bucket might be, you are curious. You're interested in hearing about R, but you're interested in RStudio and Tidycensus. Maybe you're coming from a different, maybe you're an Excel user, a Stata user, an ArcGIS user, and you want to learn about these tools. So for you, the best way to get started is use our pre-built Posit Cloud environment. So this link here, and I've also linked it in the chat, will be the way to get up and running. And so if you click there, what that's going to do is it's going to send you over to Posit Cloud. If you have a Google account, you can authenticate with your Google account. I'm already signed in here because I didn't want to go through that sign-in process, but you'll sign in. And as soon as you've signed in, you are going to see this project deployed. It'll only take a few moments to deploy. And it'll bring up a cloud version of RStudio. And I'm going to be using this cloud version of RStudio live. So basically, I'm going to be walking you through using exactly this. If you see where it says temporary copy here, what you'll likely want to do is click Save a Permanent Copy, and that will create a permanent copy in your Posit Cloud account. And so I'll be talking a little bit about setting up RStudio, but the code for today's workshop is right here. This is a script, ACS 2021 code.r, and that script is right there for you. All of the packages, the R packages, are pre-installed in your cloud project, but I do include the commands regardless. The third bucket of participants, you might not have access to a computer. Maybe you're on your phone right now and you're following along. If you bookmark these materials and you can come back to them, and I think there'll still be a lot, even if you're not coding along live with us. So let's go ahead and jump right into it. So today's workshop is all about using something called the American Community Survey. And if you're an experienced census data user in the US, the ACS is likely already part of your work. If you're coming from outside the United States or you haven't worked with census data before, the ACS might be an unfamiliar topic, but is one that you should get familiar with because it may be useful to you very, very quickly. So in the US context, we tend to be familiar with the decennial US Census, which is a complete count of the US population that takes place at the beginning of each decade. So our most recent census was 2020. We'll have another one in 2030. And that is mostly used to kind of think about congressional apportionment and redistricting. So we have fair representation of different areas throughout the United States, and also kind of allocation of resources with respect to government programs. It's important to know how many people live in the United States in different locations. But decennial census data only include a select number of questions. They ask about sex and age, they ask about race, ethnicity, and frankly, that's about it. Get a little other information about, occupied housing. But we don't get a ton of demographic information out of the decennial census. So if we want to do in-depth demographic analysis in the United States, we turn to the American Community Survey. The American Community Survey is an annual survey of about 3.5 million US households. And so it tends to cover about maybe 10 or so million Americans per year. And the ACS is so valuable because it covers a wide range of topics that aren't available in the decennial US Census. Income, education, language, detailed housing characteristics, commute, occupation. All of those questions are asked in the American Community Survey and then made available to the public as free and open data. Now, there are some particularities about the ACS that we will be discussing. The ACS comes in 2 different flavors, and then also derivative products that we'll discuss. But we can get both 1-year and 5-year ACS data. So again, the ACS is carried out every year, but because it's a survey sample and not a complete enumeration of the US population, any estimates derived from the ACS will be characterized by error. And the census won't release information if it doesn't feel that we can have confidence in using those estimates. And so the 1-year American Community Survey, so the ACS data specifically for 2021, which is the most recent data set released, we can get for geographies of population 65,000 and greater. So if there's a geography or a location with a population under 65,000, we can't get 1-year ACS data for that. 5-year ACS data, which are, you can think of as a moving average over a 5-year period. So the most recent data we have are the 2017 to 2021 ACS estimates. You can get that all the way down to the block group, which is a geography. You can think of it as a kind of collection of city blocks that tends to have about 800 to 2,000 people in it on average. A couple pieces to know about. The 2021 year ACS data were not released. They were only released as experimental estimates. So Tidycensus, the tool you'll be learning today, can't access 2020 ACS data, but we can access 2021. So there is a 1-year gap there. And as I mentioned, these are not actual counts. They are estimated counts in many cases, characterized by error. This is crucial, and we'll be talking about the significance of that throughout this workshop today. So that's a little introduction to the ACS. How do we get our data? A lot of different ways to do that. So your main interface for getting ACS data as bulk data downloads or customized data downloads is going to be from data.census.gov. And so data.census.gov is the revamped tool released a few years ago by the Census Bureau. I think they've done a really good job with it, improving it over time, making it interactive, where you can go in and download Excel spreadsheets of American Community Survey data. Data.census.gov is powered by something called the US Census API, stands for Application Programming Interface. And an API, without getting into too many technical details here with respect to data, is an interface that exposes data sets in a format such that they can be consumed by applications made by developers. And so the great thing about an API is data.census.gov consumes information from the Census API and presents it in a browsable tabular format, if that's the way you want to go. Or the Census Bureau has also empowered, by creating the Census API, an interface that allows developers to go and build their own products on top of it. And that's what I've done over in the R space. There are a variety of other interfaces to access the API. You'll be learning Tidycensus, which is an R package that I wrote to communicate in what I think is an intuitive way with this API. So let's talk a little bit about Tidycensus. Tidycensus is an interface to a select number of what I think are largely the most popular Census APIs. So the Census maintains hundreds of API endpoints with many, many different data sets available. And if you're looking for an R interface to every single Census data set, TanaRec's Census API package is a great package and a fantastic place to look. What I've done with Tidycensus is designed an interface to communicate with a select number of census data sets that are very commonly used and return them as pre-cleaned data. And you'll see how this works. It's sort of an opinionated interface to the Census APIs that is designed specifically to work with Tidyverse tools. And we'll talk more about the Tidyverse a little bit later in the webinar. It does a number of things that, frankly, it was an outgrowth of work that I was already doing. You know, I started developing Tidycensus, and I released it now 6 years ago in 2017. I've continued to maintain and update it over the years. But I was doing all this work. Originally, I was working largely in an Esri ArcGIS environment, and I would download CSV files or Excel spreadsheets from the Census website. I would need to clean that up in Excel. I would download shape files from the Census website. I would kind of figure out how to merge them together. I would format the data. This was a tedious process and a long process. And as I started to use R more and more, I wrote a number of scripts to try to automate this. And you know, with some encouragement, I think from the broader R developer community, it started to make more and more sense to release these sets of scripts as an R package. And the response of the community to Tidycensus has been fantastic. And I have, you know, brought on contributors over the years, most notably Matt Herman, who has brought in a lot of extra functionality for working with. He designed much of the microdata interface and the migration flows interface in the package. But Tidycensus, at the end of the day, just does a lot of things that to try to make it easier for you as the user community that I found tiresome. Next week's workshop, you know, it takes those shape files and it takes the ACS data, it merges them together for you and gives it back to you in a format that's ready for mapping and analysis. As you'll see today, you're getting back data that are ready to go for your analyses, at least in a format that I think is very, very suitable for that. And even some of the things that are typically challenging, conceptually and technically challenging, say when working with microdata, we have tools for handling that as well. So Tidycensus is always evolving, and you as the user community have come up with many great ideas that we've incorporated over the years, and I'm excited to see where it goes. But we're going to take it all the way back here, and we're going to introduce the basics. So R in RStudio, mentioned that briefly. R is a very popular and highly functional software environment for statistics, data analysis, and pretty much whatever you can dream up. You know, I've heard R referred to as the ultimate user interface because R has a set of core functionalities that themselves are very powerful. But R's real power is how it connects to all sorts of other pieces of software and consolidates them in kind of a single environment where you can actually do statistics, analytics, reporting, mapping, interactive charting. All of this is available to you in the same software environment, which is pretty remarkable. We'll be using RStudio through POSIT Cloud, which I mentioned. This is the premier integrated development environment, or IDE for R. And again, if you want to use that cloud environment, I'll be using it too. You can jump over to that POSIT Cloud link that I shared in the chat. If you are running this at home, go ahead and start installing some packages that are in the script. If you want to do kind of basic examples, you just need Tidycensus and Tidyverse, which installs all of the Tidyverse packages for you. If you want to run the advanced examples toward the end of the workshop as well, this is optional, but I know some of these packages are a little bit, sometimes can be tricky to configure on certain platforms. So I separated those out. If you're using RStudio Cloud, I'm going to kind of jump back in there. Those packages are already installed for you. So here we have RStudio Cloud. And what I'm going to do is just walk you through briefly how I like to use RStudio and how we're ultimately going to use it. So we have here up in the upper left corner, we have a script editor. And I do see a quick question for RStudio Cloud. All you need to log in is a Google account. So if you have a Google account, you can authenticate. If you have a GitHub account, you can authenticate with that as well. But a Google account's all you need to get it. And we'll just be working with the free tier of POSIT Cloud. So hopefully everything will run smoothly. And so in the upper left, we have a script editor, which I'll explain a little bit more in a second. On the bottom left, by default, we have in RStudio, we have the console, which you can think of as a command prompt for running R. I personally prefer to have the console on the right side of RStudio. So what I'm going to do is, you see this little window icon that says workspace panes. I'm going to choose console on right. You're welcome to do kind of whatever makes sense for you, but I like to have the console on the right side. On the bottom left then is our environment pane. This will show all of the data objects that we'll be producing over the course of this workshop. And then our files browser is here. If you've just launched Posit Cloud for the first time, look for this ACS 2021 code.r script file. Click on it to open it. It will open it here, and you'll see that. And it also has a plot viewer and an interactive plot viewer that we're going to be using in just a moment. So let's go ahead and get started. Again, if you're using RStudio or Posit Cloud, you don't need to install the packages. Those are pre-configured for you. All right, so one moment. Just going to close a couple tabs here. And so I'll be flipping between these tabs as we go. All right, so let's go ahead and get moving with this. The very first thing that you'll do is run the line library tidycensus, and that gets you up and running. So for most of tidycensus's history, it required a census API key to work. And if you're planning to use tidycensus in any sort of moderate to major capacity in the future, I would recommend getting a census API key. Tidycensus no longer requires the use of an API key, which is fantastic for teaching and fantastic for workshops, I've found. But I do recommend getting one. And so you can go ahead and go to this link to request a key. Census will email you back with a key that can be passed to the Census API key function, and it can be installed for future use with the argument install equals true. We're not necessarily going to worry about that today. I want to kind of show you how that works and what that means in just a moment. If you've never used R or RStudio before, this is how we're going to be working. What I'm going to do here is I'm going to highlight a line or a block of code by double clicking on it or clicking and dragging. When a given line is highlighted, I can use keyboard shortcuts like Control-Enter to run my code, and it sends that command, as you can see here, to my R console. Alternatively, I can click this Run button. And the Run button, you'll notice the keyboard shortcut Control-Enter appears. That does the same thing. It executes the code. And so you get a little bit of a feel for how R works if you haven't used R before, but that's how we're going to be doing things over the course of today's workshop. So let's go ahead and jump back in and start actually getting started with ACS data in tidycensus. So if you're working with ACS data in tidycensus, your best friend is this function called get_ACS. And if you're less familiar with R, what is a function exactly? This was the entire topic of my data analysis class here at TCU yesterday. So spent a lot of time talking about this. You can think of a function as like a little program or bit of code that allows you to accomplish a specific thing. You put in a set of inputs and you get an output. And so in this particular case, you can think of getACS as this little program that you can use in tidycensus that has something called parameters to which you supply arguments. And so in getACS, the arguments you have to supply are a geography and one or more variables. And I'm going to explain to you how you figure all that out in just a moment. In this particular case, I'm saying, just to translate this, tidycensus, get me ACS data at the county level of geography. For the variable B19013_001, that is the unique census code for median household income. I'll show you how to look that up in just a moment. And I want it for the year of 2021. And so Get ACS defaults to the 5-year ACS data. So this gets interpreted as the 2017 to 2021 data. The year equals 2021 is optional. That is the default year in the function. For future proofing your work, it can be a good idea to write that in, because when the new 2022 ACS data come out, Tidycensus will update and default, will always default to the latest data that comes out. So let's go ahead and try this out. I'm going to highlight this block of code. I'll click run. And literally within a second, or maybe even a half a second, I just pulled, let's look at our environment here, over 3,200 county median household income. So all counties in the United States. I just pulled all that data within a split second. That's what Tidycensus tries to do. It takes things that are previously headache-inducing and tries to make it much simpler. And so in this particular case, we get a warning message. We get an informative message saying we're using the 2017 to 2021 5-year ACS. We get a warning message that says, hold up here, you haven't supplied a census API key. By the way, you're limited to 500 queries per day without a key. So keep that in mind. 500 queries per day, I say, well, that sounds like a lot. Maybe I don't need a key. If you're a power user, I have, there are a lot of people who are hitting the API way more than 500 times. And Tidycensus it has some tools internally that if you're requesting a lot of data, Tidycensus will hit the API multiple times to get you your data set so that you don't have to. And so using a key is the way to go. But for today's workshop, it won't be required. And so taking a look at our data, there are a couple ways that we can do this. I can type in median income into my console, and it's going to print out the default structure of our ACS data. And so basically, we can look at our data here, but I'm going to jump back to the slides real quick to take a look at that in a little bit larger detail. ACS data come back with 5 columns. This is an opinionated format that I wrangle internally. This is not how ACS data come back from the API by default. Our query gives us first a GeoID. You can think of this as a FIPS code. If you're familiar with FIPS codes, it's a unique identifier for a given geography. So we have here Autauga County, Alabama. That has the GeoID 01001. We have a name column. That is an informative name for the geography that we're using. In this case, that's Autauga County, Alabama. We then have a variable column. And the variable here is B19013_001. That is our median income. And then notably, for ACS data, we get back an estimate and a margin of error. The estimate is going to be our ACS estimate. So this is the estimated median household income of households in those different counties. You can see some differences. And then the MOE is the margin of error around that estimate. And you can interpret the margin of error roughly as we think that the true value, we think that the true value is within a range plus or minus the margin of error around this estimate. And the default margin of error reported by the Census Bureau is at a 90% confidence level. So more specifically, we can say we're 90% sure that the true household income value for Autauga County, Alabama is within about $4,800 plus or minus of $62,660. So we'll be interrogating this a little bit more throughout the workshop, but I've always felt that you can't really consider estimates independent of their margins of error, because as you'll note, there are going to be some counties that have much smaller margins of error. That's because they have larger populations. And so we have more data to draw from. Whereas smaller counties, smaller populations, we're going to have more uncertainty around those estimates. And so we've looked now at the 1-year ACS data, and we get back data for every county in the United States from the 5-year ACS, excuse me. But what if you want more current data from the 1-year ACS? All you have to do is add the argument survey equals ACS1, and ACS1 is in quotes. This gives us back more current data, but it is limited. And I want to show you how that works. So if we go back here and we run this block of code for median income 1 year, you'll notice it runs right away, but check this out. Instead of 3,200 counties, we only have 841 because only 841 counties in the United States have populations of 65,000 and greater. And so if you're working in a county that's relatively large, if you're in a major city in the United States, you're going to be able to get ACS data for your county every year. But if you're in a medium to small size county, and there are many of those, I live in Texas, where there are 254 counties, and we have some counties with fewer than 100 residents. You're not going to get 1-year ACS data for that, but you can get data from the 5-year ACS for those counties. And so the format looks the same, but you'll notice we're now missing a number of counties in Alabama that we had before. I'm going to walk through a variety of other ways to pull down data from the ACS, and then we'll kind of clarify a little bit more, how things are run. And so ACS data are organized into something called tables. We're going to break down what some of this means. Like, what does this code mean? B19013_001. What does that mean exactly? So your first characters before the underscore, that represents the table name. And a table you can think of as a collection of variables in the ACS that belong to a common theme or a common topic. After the underscore refers to a specific variable, so a specific data point. Table B19001 is an entire table of household estimates by income bracket. And I'll show you how to understand what that is in just a moment. But let's say we want to get all of those data points in one bulk poll. We can do that by supplanting the variables argument with a table argument. And that will give us all of the variables with the prefix, in this case, B19001, in one fell swoop. So let's take a look at how that works. We pull this. It takes a little extra time because we're pulling more data down. And we get now a data set with 54,757 rows. We can take a look at our income table and see why. You'll notice how the data are organized. It's organized in long form. And in this particular case, we have here multiple rows per county, where each row represents a given income bracket. So this first one, that's total households. The second one is our lowest income bracket. The third one's our next lowest, and so on and so forth. You're probably asking, how do I know what the income brackets mean? I'll show you in just a moment. And so we can pull our data like that. But again, you probably want to understand how we can even figure out what those particular categories mean. So let's talk a little bit about geography and variables in Tidycensus. So geography is essential to using Tidycensus because Tidycensus from GetACS is returning aggregate data, and that data from the ACS is pre-aggregated by the Census Bureau to a wide range of different geographies. And here you see on the screen the census hierarchy of geographic units. There are a lot of them, and Tidycensus can access almost all of them. The core census hierarchy, which is the central axis of this diagram, refers to geographies that nest within one another. The smallest geography at which the Census Bureau publishes data is the census block. We cannot get ACS data at the block level. We can only get decennial census data at the block level. ACS data start at block groups. Block groups fit neatly within census tracts, which fit within counties and so on and so forth. But there are also a wide variety of other custom tabulations we can get. If you're interested in education, you might want it by school district. If you're interested in politics, you might want by congressional districts. In other cases, if you're an urban planner, you might want urban areas or core-based statistical areas, which you can think of as metro areas. And so all of these geographies are formatted a particular way in the Census API. And you can find a table in the Tidycensus documentation. I'll go ahead and actually put that link in the chat. And that will tell you how to format the geography argument to get a specific set of data aggregated to that geography. So we're using county, that's relatively intuitive, but there are lots of other geographies at which you can get data. If we want, we can also filter down things a little bit further. Like, let's say I only want to get data on median household income, but for a specific state. I can do that by using the optional state argument. So in this particular case, I say state equals MN for Minnesota, and I just get back data from Minnesota. So let's try that out. I run that code. I now got back income data for all counties in Minnesota, all 87. And one thing as well, if you want to explore your data a little bit, you can click on any of these entries in your environment pane, and it's actually going to give you a browsable Excel style table that you can use to examine your data. So I can scroll down. I used to live in Hennepin County, Minnesota when I was in graduate school. I can look at the data for Hennepin. One major motivation for writing Tidycensus, honestly, is it translates state names and postal codes internally, and it translates county names too. You can put in a county optionally as well. I never liked looking up FIPS codes. I could never remember. I couldn't even remember what they were for the state that I lived in. I mean, now I have Texas and Alabama memorized pretty much, but I still don't necessarily, I still have to look up what they all are. Tidycensus does that translation for you. Put in Minnesota or Wisconsin or California, and it's going to do that translation for you. And it's going to translate the county names correctly to FIPS codes as well, because those are even harder to remember. The variables piece is another essential one. And so looking at variables, understandably, there are tens of thousands of variables in the American Community Survey. Looking up variables is hard. I've tried to make it a little bit easier in Tidycensus with the function called load variables. Load variables takes a year or end year of a data set and a data set name. And for those two arguments, gives you an interactive browsable data set where you can go and look up variables. Just to show you briefly, this is my recommended way of parsing ACS variables to find the data that you need. It will still take some time. There's not a perfect solution to this, but this is how I recommend doing it. I'm going to go back to my script here, and I am going to create a new object here called vars using this load variables function. So I'm going to go ahead and highlight this code. I'm going to run it. Tidycensus is pulling down a data set of thousands of variables, looks like almost 28,000 from the ACS detailed tables for the 2017 to 2021 ACS. Parsing a 28,000 row data set by hand is tough, but there are a couple of different ways that you can do it in RStudio. This search box allows me to search all of the columns. So I have here the name column, which is the name of the variable. This is what you'll use in Get ACS. I have a label column that tells me what the data mean, a concept column, which is the broad sort of topic that the data point falls within, and the geography column tells me the smallest geography at which a given data point is available. And so in this particular case, we have here total population available down to the block group level. If I want to search for income, I can search for income. It's going to already filter my data down from 28,000 to 4,000. I can even do hybrid searches by using this filter button. And if I want to type in, say, median, I've now filtered down to 124 using 2 search queries to find median income information. And so once you get the hang of this a little bit more, it becomes easier. It's never going to be perfect. I highly recommend Census Reporter, censusreporter.org, where you can interactively browse variables and find their names as well. That is a great resource for getting started. A couple other pieces about Tidycensus and looking at the time, given that we did spend time on the setup, I'm going to go all the way to 2 o'clock with content. I'll break it to 10-minute break, and then we'll restart 10 after the hour for hour 2. So available data sets in Tidycensus, the detailed tables are great. In some cases, you want pre-computed percentages. You can find those in the data profile and the subject tables, and you can look up those variables by adding, say, /profile or /subject. Those are great places to look. The comparison profile for time series analysis is also a fantastic resource. We also have access to the supplemental estimates and migration flows information. There's a get flows function that allows you to access that directly. A couple comments here about data structure as we kind of move a little bit closer to the break. Tidycensus is named as such for 2 reasons. One is it's designed to integrate with the Tidyverse, which is a suite of data analytic tools developed by the team at Posit, formerly RStudio. But also, Tidycensus returns data in tidy or long format. And so the basically paper that you want to read to learn about the tidy data model and the philosophy behind it is Hadley Wickham's paper, the seminal paper appropriately titled Tidy Data. And it really talks about the design philosophy of the tidy data. I've tried to introduce a tidy model for census data that I think aligns with that philosophy as best as possible, but also makes working with the census data functional. And so what that means is that the unit, which is the row in a given data set returned by default, is a geography variable combination. So let's say I'm pulling down the age by sex table, which is B01001 for all states in the United States from the 1-year ACS. I pull that down. It grabs that data for me. And once I've pulled that down, I can take a look at it, age, sex table. And you'll notice that I have multiple rows for Alabama. In fact, I can open up the data viewer and I can see that I have rows for Alabama for each of the variables. This is long form data. So each row is not Alabama and it's not a given variable. It is Alabama for a given variable. And I found this works really, really well for tidyverse style data analytic workflows. But not everyone is comfortable working with census data this way. If you come from a GIS background like I did, you might be far more comfortable, or a spreadsheet background, you might be far more comfortable working with data in what we call wide format. Where wide format, instead of stacking the variables, it spreads the variables across the columns, giving each variable its own column. A lot of users prefer wide format because they're more used to working with data this way. And you can grab wide format data in Tidycensus. All you have to do is specify output equals wide. And this is an argument that I want to advertise to the community. I get so many questions. I see questions on message boards saying, like, I'm trying to convert to wide format from Tidycensus, And I'll tell them, did you know there's an argument output equals wide? And they didn't know. They're trying to use all these different tools to do that. And so wide format data, I'll show you what that looks like. We're pulling the same data down, but we're representing that data in a different way. If we look at the variables browser, we actually only have 52 rows in the data set as opposed to 2,500. It's one row per state or state equivalent and one column. So we have the estimate and the margin of error for each variable in the table. And I'm not saying there's a right way or a wrong way to do it. If you prefer long form data or tidy data, which I do, you have that option. But if you prefer wide form data, and I know a lot of users prefer that, output equals wide is going to be your best friend. Now, as I mentioned before, and this is something that I acknowledge, understanding what's in your data with respect to the census variable IDs, that's something that can be tricky. And frankly, I've thought about this quite a lot. Is there an easier way to do this? Should I allow users to type in, let's say, oh, I want information on the Hispanic population. Can I type in variables equals Hispanic? Tricky thing with that. And this is the reason why I've resisted it. If we go back here to our variables browser, and I try to figure out, in fact, I want to show you this just right now. Estimate total male as a variable label. There are many, many, many variables that have the exact same name. So let's say I want the male population. That seems simple. Can I just put in variables equals male? There might be hundreds of variables that are labeled that way in the ACS. How do you know which one it is? And I really don't want to see, I try to prevent against false positives in that case, where people are trying to get data for one variable, but are actually getting data for another variable. And I have debugged and helped users who have been doing this analysis before, and they've been accidentally getting data from one table that doesn't make sense. Because they weren't kind of making those comparisons. So I do enforce, you have to put in the specific variable code, you put in the legwork to find it, and you can use these browsing tools to do that. That said, once you know what you want, you can supply a named vector of variables. So if you're unfamiliar with R, vectors are data structures that can contain multiple numbers or multiple elements of text. And each of those elements, if you want, can have a name. If you name the element, so I say something like % high school equals, and this is the variable for % who graduated high school but have not done any education beyond that. This is the variable for % of people age 25 and up whose highest level of education is a 4-year degree. And this is the variable for the % 25 and up who has a graduate or professional degree. But I want to replace those variable names with a custom name that I put in. Watch how that works. If I go back here to my script, I'm going to pull down at the county level this information for California. I open that up and check this out. Instead of the ACS variable name, it shows the names that I told Tidycensus to put in. % high school, % bachelor's, % graduate. I find this to be really handy. And by the way, one takeaway before we break. I originally didn't have this functionality in the package, but a user came in on GitHub and said, it would be great if I could do this. And I originally said no. Like, well, you just use the rename tool to rename your columns. I was dismissive at first, and then I thought about it, and I thought, this would actually be a great tool. This was a fantastic suggestion. So I went ahead and implemented it. And so invariably, when you're using software like this, there is going to be functionality that you might want. And I'm not necessarily going to know what all that functionality is. File an issue on GitHub, send me an email, say, is this something that, could be added? And if I see it as something that's interesting, I might take that into consideration. These tools are always evolving. So that is your general introduction to Tidycensus. We're going to break until 10 after the hour. And you can kind of get up and stretch your legs. That's what I'm going to do. Or alternatively, feel free to play around with the code and try out these exercises. So basically, looks like that actually didn't get pushed. So apologies. Had a different set of exercises. The exercise that I would encourage you to do is try to go back and find another variable using load variables. Just find another variable. And once you've found that variable, try to go and run the code to pull down a different set of data and see if you can do that. So feel free to kind of play around with that. And apologies, it looks like I've got kind of an older version on that slide that I'll need to kind of re-push up to make sure gets integrated in. But take this code, either your ACS1 or ACS5 code, try to find another variable, just search around for it and try to find something, and then try to get your own data and see how that works. So I'll leave this slide up, and I'll see you in about 10 minutes for part 2. All right, welcome back, everyone. Hopefully you got a chance to play around with the code a little bit in the break. And Jessica and I have been going through some of the questions, and I spent some time over the break answering a few questions. But there are a couple in particular that I thought were pretty interesting that I would like to go over as a group. And so some of them, you're actually thinking in the right way. You're asking how to do things that we're going to learn how to do in just a moment. So your head is in the right place, but it looks like people are using the software pretty well. A couple of questions that I wanted to go over, and this I think is fairly instructive as we learn how to work with ACS data. And again, by the way, if you want to delve into this any deeper, of course, keep coming to the workshops, but pick up my book. Many of these questions are in there, and you'll find sort of detailed explanations. And so a couple questions that I wanted to go over. One was, I'm going to jump back here. Looking at this question. For the exercise, I chose a table B26206 that ended up only having NA values for estimate and MOE. Why would that be? Great question. And this is something that can be a little bit tricky when working with ACS data. So you recall at the beginning of the workshop, we talked a little bit about the dimensions of the American Community Survey. Basically that it is not the decennial census. It's not a complete enumeration of the US population. And in turn, we have estimates characterized by a margin of error. And the thing about that is, as estimates characterized by a margin of error, if the Census Bureau doesn't have what it sees as a reasonable sample size for confidently reporting estimates, it's not going to give you back that data. And this can vary based on geography. And so if you're seeing that, you're not doing anything wrong, because NA is the value for missing data, which means there isn't data coming back from the census. The table that was requested was B26206, which is group quarters type by educational attainment. That is a great question to take a look at. If we're trying to pull that at the county level, though, Let's take a look. So I'm going to open up my variables browser. And I am going to search for that specific table, B26206. We notice here in the geography column, it says US. That means the entire US. The geography column tells you the smallest geography at which a variable is available. In this case, unfortunately, the variable is only available at the national level. You can't even get it at the state level. And part of that is data privacy. If we're revealing too much about specific people, we're going to suppress that information in the data. It also might be a lack of statistical confidence in the estimates. And so that data only gets reported at the national level with geography equals US. So if you're getting a bunch of NAs back at a given geography, check and see in the table if that data is actually available at that geography. And it may well be that it's not. The other question that I got, and this is a really good question that you want to know about, and it'll actually answer a couple different questions in doing so. One user said, I'm trying to find variables from the data profile, and I can get them. And these are variables from the data profile, by the way, in GetACS, but I can't find them in the vars table. So load variables talks to different data sets at a time. It doesn't load everything at once. If you put in load variables, as we did here, 2021 ACS 5, it gives you the detailed tables, which are the most granular tables available. For the data profile, I'm going to make a new object here called vars_profile. I'm going to do load variables 2021 ACS 5/profile. So that's what I was talking about when I was on this slide here. If you're trying to pull variables from the data profile, add /profile. From the subject tables, add /subject, and so on and so forth. And so if I do that, here I have vars profile. I can open that up, and I only have 1,300 variables that I'm working with, so I can browse that a little bit easier. And now I get access to kind of thinking about the data profile. A follow-up question was, can I get data for multiple years at a time? And the answer is no, I don't allow that. And why don't I allow that? Couple of reasons. One is logistically, because it could be done. One is logistically that, we have the 2021 year ACS, which in and of itself isn't accessible in Tidycensus, and the breaking of that time series, it does throw an error to tell you that, but that's just something that would introduce some additional complexity for users, in my opinion. The other and more important reason, and I encourage you to read the section in my book I have 2 sections in my book on this topic, but working with time series census data is something that you need to be very intentional about. And the reason why is that variable names can change over time. In the detailed tables, they won't, but sometimes there are variables that appear or disappear over time in the detailed tables. So we might have a variable that's available that wasn't available 5 or 10 years ago. And so if you're trying to build a time series, that's not going to work. For the data profile on the subject tables, and this is critical, the variable names themselves can change. And so if I'm trying to pull data for multiple years for the same variable name, it might represent something totally different. So let me show you. Probably the most common variable that I pull as an example in the data profile, and as such I have it memorized, is DP02_0068P. And that's the percent of the population age 25 years and over with a bachelor's degree or higher. So this is a pretty common, social characteristic in the US to analyze. And so, this is something that, and it's pre-computed, which is fantastic with an appropriate denominator. That's great. But what if I wanted, but this is for 2021. What if I wanted to know that information for let's call it 2016? And I go back and I pull the data profile. I'm going to make a new object called bars profile 16, and I'm going to load the same variables, but for the year 2016. So this will be for the 2012 to 2016 ECS. I pull that in. I already notice I have fewer variables, only 1337 instead of 1354. And I go in, grab this variable, and I'm going to look for this variable and check this out. In 2016, that same variable that meant percent with a bachelor's degree or higher actually meant percent civilian population 18 years and over. Totally different. And you might say, well, why would this happen? Census is upfront about this, that the names change in the data profile. And this is something that when I first started working with Census and ACS data, I was working on a project and I was trying to do, originally I considered allowing multiple years in Get ACS. And I think I was experimenting with that and I was just getting nonsensical results. Like one year would be what appeared to be a percentage, another year was what appeared to be a count. It didn't make any sense. And digging in a little bit deeper, notice that there's this inconsistency across years. And so there are tools, and I have a section in my book that are a little bit more advanced that show you how to pull down a time series if you're confident that you know that the variables aren't changing. Or you can alternatively use the comparison profile, which is nice. The comparison profile has 5-year comparisons. Now it goes down to the county level, but it has 5-year comparisons for variables. So you can actually make those time series comparisons. So really, really good questions. And hopefully that clarifies a couple of these questions. So let's jump back to the script. I'm going to close out some of these objects. One thing I do want to give you all a heads up about if you're using our Studio Cloud only gives you 1 GB of memory. You have to pay for more to get more memory. I've tested this out and we're going to do a memory refresh before the 3rd hour just to make sure we're good. But if you do need to refresh the memory because you've been playing around a lot, you can click Session, Restart R, and that's going to refresh your memory. You can also clear all your objects out that you've created by clicking this little broom icon, and that's going to clear up some memory as well. So if I click this little broom icon here, it gives me a warning that says, are you sure you want to get rid of them? I'm going to say, yeah, that's fine. And it's going to empty my environment and it's going to clear up some memory. So that's just a heads up if you're running into that. So my project refreshes and I'm gonna get moving on this. So let's jump into part 2, which is analyzing and visualizing ACS data. So if you've worked with R before, you're likely familiar with the tidyverse. If you haven't worked with R before, the tidyverse is a set of kind of integrated R packages developed by the team that Hadley Wickham leads at Posit, which is formerly named RStudio, to try to streamline the process of data analysis and visualization in R. The tidyverse is my preferred way of doing work. I've designed Tidycensus to integrate as best as possible with the tidyverse. It's not everyone's cup of tea, but the beautiful thing about R is there are multiple different frameworks that you can use for doing data analysis. And one thing that I really like about the tidyverse is it offers a set of expressive functions or expressive verbs that allows you to kind of clearly specify what it is that you want to do in your data analysis. We're only going to scratch the surface here. I'm not going to get into a kind of massive amount of detail. And But something that I will be getting into in this particular section is thinking about how we can start to play around a little bit with these tools. Now, thinking back of kind of what I just did to show you how the environment was cleared, and that's only if you needed to do that. But let's say you went in and did that because I showed you how to do that. You will need to repopulate the median income data set here at the very least to run these first examples. So I'm going to go back up here because I deleted it. And I'm going to go and grab my median income data set again. So you want to make sure you at least have that median income data set available. If for some reason you're trying to run the examples, maybe you removed it, and go ahead and just grab it again. That is one of the beautiful things about working in a code-based workflow. I lost something. Hey, it's in my script. I have a trace of it. I can go back and get it. And so let's jump back in here and talk about how Tidycensus and the Tidyverse work together. So we talked about the distinction between long and wide format. My goal was to kind of return data in long or tidy format because Tidyverse tools are really built to work this way. And again, we're going to scratch the surface here. If you grab a copy of my book and you look at chapter 3 is all about workflows for using the Tidyverse with Tidycensus. So there are tons and tons of examples in there if this piques your interest. So let's take a look at some examples of how we explore data, and maybe we'll do some custom examples as well. So let's take our median income data and just think about maybe some basic questions that we want to ask of the data. There are a variety of different tools, as I said, reasonably expressive verbs or functions that allow you to reshape your data, move stuff around, analyze and summarize your data. I'll show you a few such examples today and give you some pointers for taking your work even further. So let's ask some basic questions of our data. And, honestly, it's always interesting to me, and this is part of my philosophy, even in my data analysis teaching. Students will come in and they'll be hearing all of the latest hype about, oh, machine learning algorithm, this, AI, that. And having consulted for years across a wide variety of businesses, so many questions can be answered by having efficient workflows for just saying, what's the biggest value? What's the smallest value? What's the biggest value for this subset of data? I mean, those are the questions that come up again and again, and the Tidyverse is built to answer those questions. So let's take a look at this. What if I want to know, among all the counties in the United States, what are the counties with the lowest median household incomes? And what are the counties with the highest median household incomes? Well, I have the arrange function in the dplyr package, which is part of the Tidyverse. So let's take a look at how to use this and how to use the Tidyverse in general. I'm going to jump back here to RStudio Cloud and scroll down in my script to part 2. First and foremost, I'm going to load the Tidyverse. And when I load the Tidyverse, you'll notice I get this message here on the right-hand side. Attaching packages and any conflicts that come up. The packages that are attached are actually 8 different packages. The Tidyverse is a whole family of packages, a core set of packages, and then an allied set of packages. The core set of packages are a series of packages, again, developed primarily by the POSIT team to do a wide range of common data analysis tasks. Today, we're going to be focusing on 3, the dplyr package, the tidyr package, and the ggplot2 package. So let me walk you through what these packages are. ggplot2 is the most popular framework in R for data visualization. We're going to walk through a step-by-step ggplot2 workflow in just a moment. Tibble is an extension of R's base data frame class, which is how rectangular data sets get represented. It just makes it print a little bit nicer. So if you'll notice here, if you were wondering what a tibble was, it is a rectangular data structure that is basically an R data frame, rows and columns, but it has some special abilities. It prints out only the first 10 rows. It tells you how many rows there are in the data set, and it tells you what the type of the different columns are. So these are character or text columns, and then these are double, so they're numeric columns. TidyR is used for reshaping data. We'll use a function in TidyR in just a moment. ReadR is used for reading and writing data sets from a variety of sources like CSV files. Per is for functional programming and iteration. That is a more advanced topic. But again, take a look at chapter 3 of my book for a little tutorial on how to use per with census data. A little hint, if you are brave and you want to go and you know that you can grab a time series of your data, PERS is going to be how you do that. So take a look at that. Dplyr is the main data wrangling package. You can think of it as bringing in a lot of SQL type functionality, database type functionality to R. So querying your data, subsetting it, renaming columns, things like that. And then stringer is used. We'll use a function from stringer in a little bit to do text manipulation. And then forcats is used to handle factors, which is beyond the scope of what we're discussing today. So the tidyverse gets you all of those tools in one fell swoop. And it loads in all, when you do library tidyverse, you're loading in all of the functions and making all those functions from all these packages available to you. So let's try this out. The arrange function sorts your data by default in ascending order of one or more columns. And so what I'm putting in here is I'm using this arrange function. The first argument here is my data set name, median income. The second argument here is the column, and you can put in multiple columns if you want, but the column that I want to use to sort the data. I want to sort based on the ACS estimate. So let's run that and see what we get back. It sorts my data in ascending order of median household income and shows me those counties or county equivalents that have the lowest median household incomes. We notice that they're all in Puerto Rico. They're all municipios in Puerto Rico. And so you might say, well, that makes sense. The economic circumstances of Puerto Rico are very different from, say, the 50 states from DC and Puerto Rico. It's not apples to apples because Puerto Rico is a territory, not a state. But Puerto Rico does come in base queries and get ACS. So and I did see a couple questions where people were saying, well, I just want to get the continental 48 states. How do I do that? I'm going to show you in just a moment. So we see that these county equivalents in Puerto Rico are those counties or county equivalents with the lowest median household incomes in the US. Let's take a look now at how to do it the other way. I'm going to sort my data in descending order. And so descending order, we use this desc function. So by default, we're sorting our data in ascending order. Instead, if we want to sort our data in descending order, we wrap the column that we want to sort in descending order with this desc function. And if I run that, you'll notice it prints out a different set of counties. I'm taking all of this information on counties in the United States, and I'm sorting now in descending order of median household income. As we can see here, it's very kind of Bay Area and Washington, D.C. dominant in the top 10. So Loudoun County, Virginia comes in at number 1, median household income of over $156,000 per year. Falls Church City, Virginia. So Virginia has, if you're from Virginia, you know this, independent cities as well as counties. So Falls Church City comes in as number 2. Santa Clara County, so Silicon Valley, San Mateo County, they come in, and then Fairfax County comes in at number 5. So a lot of DC Bay Area coming in as the highest median household incomes in the US. And on the one hand, this is a fairly simple analytic task. It's the first analytic task I teach in my data analysis class, but it is something that is extraordinarily powerful. What is the highest performing or the lowest performing in my business, that sort of thing? What is the most extreme value of this if I'm analyzing demographic data? The Tidyverse brings in this functionality to try to make that smooth. So we've taken a look at this, but in many cases, as an analyst, you're going to want to think about ways to refine your analysis. We're trying to figure out, okay, I have a set of questions. I'd like to answer that question. How do I design a workflow to appropriately do that? And we're going to get into these workflows just a little bit. There's only so much that we can cover. Even though it's a 3-hour workshop, there's only so much that we can cover in that amount of time. But if we start to piece together different sets of tools, and this is why I love the Tidyverse, these tools fit together in a way that allows us to answer so many of the questions that we're interested in. I had 2 questions in the Q&A that said, I just want data for 48 states. How do I do that? 2 ways. One is, you can actually, when you're querying the data, put in multiple states. So if you had a list of states for which you wanted to query, you could do that. So if I'm going back to part 1, you'll notice I had Minnesota income. I chose state equals MN. If I want to do something like multi-state income, and instead of MN, I would use the C function to define a vector of states. And I could do something like, let's do Michigan, Ohio, West Virginia, and Kentucky. Let's do those. I can put in multiple states. I can run that. And you'll notice this message prints out that says you're getting data for multiple states. And now if I look at my data, it's only for those states. So here's Kentucky, here's Michigan, here's Ohio, and so on and so forth. So that's one way to structure that. However, if you want data for the 48 continental US states, or alternatively, in this case, if we're looking at an analysis where we're saying, okay, those are the lowest income counties in the US, but Puerto Rico is a territory, it's not a state, and so maybe it's not apples to apples. How do I figure out what the counties, the lowest income counties that are within states specifically, how do I do that? You might want to go the opposite direction. You might want to pull down all the data first and then do something called filtering. The filter function in the Tidyverse allows you to do that. And you can think of the filter function as like a SQL query, where I am asking a data set a question and I'm getting back a result based on the question that I asked. And so what filter takes, I'm basically saying, I want to create a new data set. I'm going to call this income for states in DC. I want to filter the data set, median income, for some expression. And I can put in any expression that I want here that evaluates to true or false. And so I could do something like, give me all those counties with an income above 100,000. And I would do, I'll actually show you how to do that in just a moment. In this particular case, I'm doing something a little bit more advanced. So the not equals operator in R is the exclamation mark. The stringer package, which I mentioned before, allows us to do string search and string manipulation. And the str detect function scans a string or scans text to check for the presence or absence of a given phrase. So you can read this as look for all of those rows in the median income data set where the phrase Puerto Rico is not found in the name column. So we're getting rid of everything in Puerto Rico in this example. We then can sort that data set, which I'm going to do right now. And we notice we've eliminated Puerto Rico from our data. And we only get back counties in the 50 US states plus DC. So this is pretty powerful. As I said before, like let's say you want to know how many counties in the United States have an income above 100,000. I could do counties above 100K is filter median income estimate greater than, or we'll do greater than or equal to 100,000. I run that. Looks like there are 68, only 68 have a median household income above 100,000, and I can browse. As you get more experienced with this, you're going to want to start stringing together some of these methods, some of these functions into coherent workflows. And a common workflow is understanding sort of how subgroups vary within, within a given data set. This is extraordinarily common. And Tidycensus tries to set up pretty well to do group-wise data analysis. Chapter 3 of my book has a lot more information, but I want to share one such example that I think is pretty interesting and talk you through kind of a tidyverse style analysis. So group-wise data analysis is handled in the tidyverse with the group by and summarize functions. And with the latest version of dplyr, there's actually additional kind of brand new ways to do grouping. I'm not talking about that today because I haven't even fully integrated that into my work yet, but for more experienced R users, you may want to take a look at it. And so the whole idea behind Tidycensus, or at least one of the big ideas behind it, is with long form data, you can use that variables column, or you can use other information in your data to identify or define groups pretty readily. And then you can break that information down using the group by statement and then summarize your data in a way that allows you to do some interesting analysis. So I want to show you how we can put some of these pieces together in something that's a touch more sophisticated. Let's say we want to ask the question, what is the highest income county in each state? So you have all that data, but that's not something that you can just easily figure out by browsing manually. That's going to take you a little bit of time. So how do I figure out the highest income county in each state? Let me talk you through how some of these tools work. I'm going to first go back here and we're going to look at our median income data set. There's a lot of information in here, but we're going to need to create some information as well to answer this question. The GUID column has information about the state. The first two characters here are actually the state code in any county code. So we could use that. But also in the name column, you notice every county is followed by comma space state name. So the state name is included in the name column of our data set, which means we can get that information out if we know how to extract it, because there isn't a specific column called state just yet. But let me show you how to do that. The separate function in the tidyverse is built for this sort of workflow. We're going to separate the name column into two new columns, and it's going to look for every place where it goes comma space in the name column and separate it out into county and state. You'll notice this funny looking operator here. That's called a microdata pipe. And there are two types of pipes in R. One is this tidyverse microdata pipe, which is percentage sign greater than percentage sign. There is a pipe that ships with base R now as of R 4.1, which is the regular sort of pipe operator and then the greater than operator. Both work fine. It's recommended to read this as then. So this reads as generate an object named highest incomes, where we take the median income data set, then we separate the name column into county and state, then we group by our brand new state column, then we filter our data, so we're subsetting it for only those rows where the estimate column is equal to, using the double equal sign, the maximum value of the estimate column, which will be honored by group. So let's see what this does. I run the code, and I'm gonna now look at my highest incomes data set. I have 51 rows. And in this particular case, I have the highest income county per state. So interesting stuff there. That's how you put together a more sophisticated workflow. You know, I do see kind of one question, got you know, some interesting questions there that we've got that we can come back to in just a second. So, all right. Let's go ahead and keep things moving. And we'll take a look at visualizing ACS data in the last 15 minutes that we've got. So visualizing ACS estimates, there's a ton that you can do with data visualization and demographic data. And in fact, we're going to spend a lot of time in next week's workshop thinking about how to analyze the geographic characteristics of ACS data with maps. So we're in some ways doing more with visualization next week than we're doing today. But I do want to take you through a workflow for visualizing data from the ACS that takes into account the unique properties of ACS data. And so ACS data, as I've said many times in this workshop, are characterized by margins of error. They're characterized by uncertainty, which means if we're thinking about rankings or comparisons, we need to be careful because some comparisons can actually appear misleading. There might be an estimate that appears higher than another one, but if the margin of error is large enough, well, those estimates might not actually be statistically different from one another. And so we need to account for that. How do you represent that in terms of visualization, where you're showing one data point here and one data point here? I want to introduce a workflow for doing. And what we're going to do is we're going to walk through building a visualization with ggplot2 that does just that. And we're going to go step by step here to show what you can visualize with ACS data by default, and then how you might want to do a little bit of cleanup to fix that. And so let's take a look at this. We're first going to grab some sample data on median gross rent by county or county equivalent, because Baltimore City is an independent city in Maryland. So we'll use some familiar syntax. Geography equals county, variables equals the code for median gross rent, state equals Maryland, and then we'll put year equals 2020. So let's go ahead and pull that data down. I'm going to take a quick look at my MD rent data set. And as we see here, it's the familiar structure of data returned by GetACS. So I want to think about some visualization that makes these comparisons. We can see that median gross rent in Allegheny County is $719 per month, whereas in other counties like Anne Arundel County, it's $1,000 more than that. I want to think about a way to represent those differences graphically. And there are tons of ways to do that. You might think about a bar chart, which would be one way to do that. One of my favorite types of charts is called dot plot, which is like a bar chart, but you're only representing the specific data point. You're not drawing the actual bar. So you have, generally speaking, one categorical axis and then one numeric axis. And so you're comparing categories across some metric. And the categories here are going to be the counties, and the metric is going to be median gross rent. And we can do that, for starters, with ggplot2 on a very basic level. So in ggplot2, we invoke the ggplot function to initialize our visualization, and then we specify a data set that we're visualizing, which in this case is MD rent, and then an aesthetic. And we put the aesthetic inside this function called AES. And the aesthetic, or the aesthetic mapping, it maps different elements of your data, different columns of your data, to different elements of the plot. It could be the x-axis, it could be the y-axis. That's what we're doing here. It could be the color of the shapes on the plot. It could be the size of the shapes. It could be all sorts of different things. So there's a whole lot that you can do that goes way beyond what we're covering today. In this particular case, we're just mapping the ACS estimate to the x-axis and the name to the y-axis. We use the plus operator to link that to another kind of layer in our visualization, and we specify a geom. We're drawing points, we're drawing dots to make a dot plot. So let's go ahead and draw it. You'll notice here in the plot viewer, in our studio, we get a plot. The plot is a plot. It does show us information. We can see here, it looks like the highest median gross rent is in Montgomery County. The lowest looks like Garrett County. But the rest of the plot, frankly, by default, it doesn't do a lot for us. ACS data are great. Tidycensus data are helpful. They can get you to a point. But once you have that data, you still need to make decisions about how to communicate, because there are going to be so many different ways that you can communicate this information. I'm sure you're looking at this plot right now, and hopefully you're thinking, that's not a good plot. And I can think of a few ways to improve it. And I've got a few recommendations here, and there are probably even more ways that you can tinker with this and make it better. But looking at this plot, what's wrong with it, and how do we make it better? First, the dots are all over the place. The data were not sorted by value. That makes comparisons really difficult. I was able to find the highest and the lowest, but everything else was just a mess. The axis and the tick labels are not intuitive. I know what an estimate is because I'm the developer working with the ACS data. If I show this to someone else, does this tell them what that is? They have no idea. The name, that's sort of self-evident. The y-axis labels as well, they have repetitive information on it. Everything's in Maryland. So we don't need to say Maryland over and over and over again. That is overkill. And we've made no attempt to customize the styling. Now, ggplot2 has attractive defaults, and that is one major benefit of working with that software. But if you're just using the defaults in your visualization software, you might want to think about some ways to customize to make it your own and show a stakeholder that you're putting in additional effort. So let's talk through how to fix this. First things first, we're going to do two things. We are going to use the reorder function to sort our counties by the value of their ACS estimates. This is going to make a massive difference. We're going to change the color as well and the size of our dots, but it's really the sorting that's going to make the huge difference. So watch this. We have here this visualization. I'm going to iteratively assign updates to the plot to an object named MD plot, and we're going to see how it changes. So I'm going to run that, and then I'm going to type MD underscore plot. And so I go from this to this. Now the chart isn't perfect yet, but now just the sorting of the dots makes a massive difference, because then I can actually get a sense of a relative ordering or ranking. Oh, I see Howard County and Arundel are up at the top. I see kind of Somerset and Allegheny are down at the bottom. That was difficult to parse before. So that resolves one issue. In my next step, now I want to clean up those tick labels. It wasn't clear what the data values meant, and I had that problem where I had repetitive County Maryland, County Maryland, County Maryland. In the scales package, there are a lot of built-in formatting functions that allow you to format your tick labels pretty much however you want. Or if you're a little bit more advanced, you can specify a custom function. If you're just getting into R, this reads as, for every label, which we'll call X, remove either space County Maryland or comma space Maryland because of Baltimore City. If I try that out, now I type MD plot. Look at the difference this made. I went from this, in which, look at all that space County Maryland's taking up in my plot, by the way. I go from this to this, much cleaner. And I'm labeling median gross rent as actual formatted dollars. So someone can look at this and they can know what that is. In my next step, I want to do some additional cleanup. I'm going to change the theme of my plot to a minimal theme with a white background. And I'm going to add some informative labels with this labs function. I'll give it informative title, a subtitle, a caption, and then some more informative, or maybe even remove the axis label entirely. So I'm going to run that through here. And take a look at how my plot changes. I've removed that gray background. My red dots really pop out. All of plots, by the way, in our studio are SVGs, or scalable vector graphics, so you can resize as much as you want. And now I have a much cleaner look, a much cleaner looking visualization. But as I mentioned, this ranking, because it's ACS data, can be misleading. If you look at this, for example, I'm comparing some of these estimates here. You look at, say, Queen Anne's, Calvert, Frederick, St. Mary's, all those dots are really near to one another. And it says that, say, Queen Anne's is higher than St. Mary's, but is it really? I'm not going to run this code specifically, but if you actually look at this and the margins of error around this, Calvert County, for example, has a margin of error of $113 around its estimate of 1526, which means Calvert County might actually be higher than Prince George's County, and it might actually be lower than St. Mary's County, given the margin of error. We don't know. And so this is something that's important to take into account. And so how do we visualize uncertainty in an intuitive way? ggplot2 allows you to draw error bars. So if you pretty much, I'm rerunning this whole thing, but I'm adding in some error bars where the left side of the error bar will be the estimate minus the margin of error, and the right side will be the estimate plus the margin of error. If I do that, I can go back here and show you how that changes. I like to call this, if you're a Star Wars fan, like a TIE fighter plot. It looks like little TIE fighters, but it's really informative. As I see here with Calvert County, this is the point estimate represented by the location of the dot. But those wide error bars show me the uncertainty as well. And so this is, I think, very helpful at communicating that information. And what's cool about this, given how we set it up, we actually have a time series where you can use your little arrows in our studio to click through. Click, 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 click. And you can see how that plot sequence changes. In the last bit of time before we break, and I think I'm going to go until about 5 after the hour, and then we'll break until 15 after the hour, because I want to show you a couple of these pieces. I've mentioned R as the ultimate user interface. And as you can see, R can do a lot of things. You take your ACS data, you can analyze it, you can visualize it. But the number one reason I actually got into R, because I tell this to my students all the time, I took a class in R in grad school. I didn't like it. It was not intuitive to me at all. It was not taught in a way that I could really understand. And so I put it down for 5 years and didn't come back to it until I started wanting interactive graphics to use in my teaching. Probably many of you know the Gapminder Hans Rosling plots. I wanted to make moving bubbles. And I came across JavaScript and d3.js, and I struggled with that. But I found that R actually had some packages that allowed for the creation of interactive graphics. And that's how I got back into R. Creating interactive plots by hand can be challenging, but there are a number of packages in R that allow you to take your ggplot2 plots and make them interactive with a minimum of code, which is fantastic. One such package is the Plotly R package. There's a book on it that's linked in the slides. I encourage you to take a look at. And it's an interface to the Plotly JavaScript library. There's a function in there called ggplotly that automatically converts and intelligently converts your ggplot2 graphics to interactive plots. Let me show you how this works. I am going to take my error bar plot, and I'm going to use the ggplotly function in one line of code. It takes my error bar plot. It looks similar, but if I hover my cursor over any of these points, I get the actual data value. The cursor itself, let's say I want to compare these points, I can zoom in and only show specific areas. I can zoom back out. I can zoom in here if I want to. I have a richly interactive chart that has taken my ggplot2 graphic and made it interactive. It is fantastic. Another package that I really like is called ggiraffe. And the way that ggiraffe works is it also sits on top of ggplot2, but you specify special interactive geoms when building the plot. So I might say something like, I want to build the same plot, but I want interactive points. I'm going to use, instead of geom point, I'm going to use geom point interactive. And then I can render that as an interactive plot, and I can customize some of the interactivity. ggiraffe is a fascinating and really full-featured package for interactive data visualization. I have a few examples of how to use it in my book, and I'm going to show you next week how to make interactive maps with it. For now, just to kind of show you, as you're learning this stuff, the potential of what you can do. All this code is the same as what we did before. It's just all pieced together. But I'm using here geom point interactive instead of geom point. I then send that interactive graphic to this giraffe function to render it as an interactive chart. And you'll notice the styling. You'll have to fiddle with it. Not everything always carries through. This might be in our Studio Cloud thing, but I can hover my cursor over the different points. The points are highlighted in cyan. And I get a hover tooltip that shows that median gross rent value. So lots of interesting ways that you can extend your work. And the final bit that I have is, if you want to save your graphic as an actual standalone HTML file that you can embed in your website or your portfolio, it's fairly straightforward to do that. The save widget function in the HTML widgets package allows you to write that to a standalone HTML file. And you can even do this right in our Studio Cloud. I'm going to go ahead and run this code here. I've just saved out my Plotly plot as a standalone HTML file. I can open this up in my web browser. And I need to resize it a little bit, but make sure that everything is visible here. I need to resize that a little bit, but you can see that I actually have an interactive chart. Now, this isn't a chart that's intended to be displayed on a giant monitor like I have in my office, but if you're embedding this, say, as an iframe in your website, it's going to look pretty good. In fact, I have that in the slides right here in the same chart. All right, so let's go ahead and pause there for part 2. Here are some exercises that you can do if you'd like, and I'm going to look through the questions as well. So take a variable swap in a variable for the analysis in this section. Try to rerun it for a different variable. I'm suggesting percentage with a graduate degree. You're welcome to choose whatever you want, and try to answer some of these questions. Which counties have the largest percentages? Which counties have the smallest? Pick a state and see which county in that state of your choosing has the highest percentage. If you have time, if you'd like to challenge yourself, try to make a margin of error plot. And then ask yourself if the margin of error plot works well. And just as a heads up, Maryland has a handful of counties. A margin of error plot for Texas with 254 counties maybe is not going to be all that intelligible. So, these are interesting questions where we kind of learn these principles on a case by case. But let's break for 10 minutes. We'll come back at 3:15 Eastern time, and we'll finish up by discussing ACS microdata. Looking forward to that. All right. Welcome back, everyone. I hope you had a restful break and you were able to maybe play around with some of the exercises a little bit. Got some really good questions that I do want to go through. Some of you are very astute users who are looking to push this even further, and that is great to see. So I'm going to start just with one general question that has come up. Thinking about the future workshop, I think there are a number of participants who have asked about the Python workshop in 2 weeks. And if it's beginner friendly, or if you need to know anything about Python. No, you don't need to know a thing about Python. I'm going to have a pre-configured environment for you that I will show you exactly how to get up and running. And we will start from the ground up. And if you've been looking for an excuse to kind of get your feet wet with Python, or you're curious about Python, and you would like to learn a little Python using a topic that is, I think, interesting and maybe familiar to you, which is census data, then check out that workshop in 2 weeks. I think it'll be a great introduction to that. And, we're not assuming any kind of extensive prior knowledge. Just bring your curiosity and you'll get something out of it. A couple of technical questions that I think were really, really good that I want to show you. One is maybe kind of pushing things a little bit further from a technical standpoint. And another is an example gotcha in data analysis that a couple really astute observers found. And I want to show you how to get around that. So one question was, how do you take this here and remove multiple states? How do you do that? That requires, some alternative approaches where, we can find let me just kind of walk you through, I suppose, as I explain it. So I've got, a couple people are saying, okay, let's say I want to remove, like, say, 2 states. I want to remove Minnesota and Iowa. How do I do that? I can maybe go 2 different ways, and either one is going to be appropriate. And the thing is, in R, there are a lot of different ways often to do the same thing. So let's say I want to get rid of Minnesota and Iowa from median income. And so I have my median income data set. I could try something like this. I'll call it income subset. And I'll make that filter median income. And here I'm basically, I want to get rid of Puerto Rico, but what if I want to get rid of Minnesota or Iowa? I could specify that in this string. I could go Minnesota or Iowa. And this is basically saying, okay, I'm going to search for Minnesota. I'm going to use this OR operator. I'm going to search for Minnesota or Iowa. And I'm going to get rid of those rows. And so in this particular case, what we have here is we're starting out with all of my counties and median income. I make my filter subset, my income subset, and you'll notice I've gotten rid of about 100 counties. I've removed all the counties in Minnesota and Iowa, and I can confirm that by searching the name for Minnesota, and there are no matching records. So that's one way to do it. Another way to do it is a little bit more almost tidyverse style, where I create a state column, and then I filter out those rows where the state column matches Minnesota or Iowa. So this would also work. I could do income underscore subset is starting with median income. Then I'm going to use this code here, separate into a county and a state column. Then I'm going to filter for where the state column is not in, and this is a special operator that if you're learning R, you want to know about. Percentage sign in, word in, percentage sign. Special operator that allows you to kind of look inside or sort of like look inside a set of values or sort of match values with one another. It's really handy. I use it all the time. Minnesota, Iowa. So you can read this as separate my name column into county and state, and then filter for only those rows where the state value is not in this set of values. I run that. You'll notice that runs the same. So one thing that was interesting, and this is one of the vagaries of working with census data, when I ran this here, and I was filtering out any county that has Minnesota or Iowa in its name, I get 3,034. If I do this process where I'm specifically filtering out counties in Minnesota or Iowa, I get 3,035. Why the difference? There is likely a county in the US that has Iowa in its name. I don't know where or what it is, but those are the little pieces that can sometimes come up. Another question, and this was an awesome question. A couple of student observers ran this code for highest incomes and looked at it, and they tried to find Texas, and it wasn't there. Why? It's because we did something that actually eliminated Texas from the data set without knowing that we did it. So here is a little thing about R, and this is essential for your work with census data. So the tricky thing with any sort of ACS data, And we can look at, for example, our median income data set. I'm going to sort on here. I'm going to go all the way down. If a county is too small or a geography is too small, Census will suppress that estimate because it doesn't have a large enough sample size to actually draw an inference. Loving County, Texas, as I mentioned, my state of Texas is chopped up into 254 counties, some of which Loving County included. Loving County is this, I want to say it's either now the first or second smallest county by population in the US. Kalau County in Hawaii, which is a former leper colony on the island of Molokai, I think is the smallest. But Loving County is one of the smallest. It's tiny, has fewer than 100 residents, which isn't enough households to get a median household income. And so the estimate is NA. If we have an NA in a calculation, R cannot do that by default. It flags it, says, well, we don't know what the maximum is because one of your values is unknown. So it returns NA, which means we didn't get back a result for Texas. To fix that, we need to, inside of the max function, put in na.rm equals true to remove NAs, which means give me the maximum and ignore Loving County. And if we rerun that, we now can look at our highest incomes data set. And there's Rockwell County, Texas, which is not too far from me in the Dallas-Fort Worth area with the highest median household income. So that was a great catch from some of our participants. And that was a great learning experience. Iowa County, Wisconsin. Good one. That's our trivia question for today. Iowa County, Wisconsin. Love it. All right. So let's dive in. So what I'm going to do here is I'm actually going to refresh my workspace. I'm going to clear my objects. I'm going to refresh my workspace. I'm going to restart R. If you're on your own computer, don't worry about this. If you're on our Studio Cloud, you may not even need to do it, but I'm just being a little bit careful about it because we're pulling some microdata, and that can sometimes be a little bit bigger. So I'm going to scroll down here to part 3, working with ACS microdata, and I'm going to jump back to the slides. So, seconds. Right. So what is microdata exactly? If you haven't used microdata before, you're in for a treat. This is a data set that I've been using for many, many years, way back to my undergraduate days. And when I had the opportunity to get it into Tidycensus, I was absolutely thrilled. So microdata are individual level responses to surveys. And microdata are available across a wide range of government surveys. If you work with transportation, the National Household Transportation Survey has microdata. If you work with, say, energy consumption, there's the Residential Energy Consumption Survey from the Department of Energy in the US. They have microdata. There's health microdata you can get. There are a lot of different microdata sets that are available to researchers. From the ACS, we can get the PUMS, which is the Public Use Microdata Series. And when you have individual level information, you can create detailed cross-tabulations that aren't available in aggregated data. It's really, really cool. So the thing about the PUMS data is they cover a smaller sample size than the aggregate data. So you might end up with slightly different tabulations than you would get in the aggregate data. The aggregate data will be more reliable because it has a larger sample size that it's drawing from. But working with microdata is really great because it allows you to get custom tabulations that you can't necessarily get in the published tables. You can download bulk microdata datasets from the Census FTP server, or you can grab it from the MDAT tool on data.census.gov. The IPUMS project at my PhD alma mater, the University of Minnesota. When I was in grad school, I was a fellow at the Minnesota Population Center, which maintains IPUMS, is really the premier resource for working with time series microdata. And it's really a great resource that I've used for many, many years. If you use IPUMS already, you might say, well, why would I want to use Tidycensus? Well, for one, you might want to stick with IPUMS. That it's a great resource, and I won't disparage it at all. But an advantage to using Tidycensus is you can access the data programmatically and stream it right in from the Census API. And we have an integrated set of tools as well for handling the complexity of the PUMS data that I think are really great. And so I'm excited to show you that stuff. So how do you use microdata in Tidycensus? We have a function called getPUMS, and I originally wrote this function years ago, but it was really my co-author Matt Herman that supercharged this. Like, he actually made this stuff work, and a lot of the stuff that you're seeing is stuff that he developed 2-3 years ago. The getPUMS function talks to the ACS microdata API, and it pulls in individual level ACS records. You'll specify one or more variables, and you'll notice that the variables are more intuitively named in the PUMS than they are in the regular ACS, and a state. You can do state equals all to get all states. This can take a while. The 2017 to 2021 5-year ACS has, for the entire United States, has over 16 million records in it. It's a lot. You can download it. Tidycensus will help you do it. And we even have error handling built in so that you can try to avoid API hiccups. And you can get all 16 plus million records from Tidycensus. Takes a few minutes, understandably, to get. I don't know if, but if you need that bulk download, you can do it. The function does default to the 5-year ACS, but you can also get 1-year ACS data. So just like the published tables, microdata come in those different flavors as well. Same with the published tables. 2020 1-year ACS data is not available. So let's try grabbing some data. We're going to be grabbing data for Hawaii. We're going to get data for sex, age, and household type. That's what those different codes mean. We're going to pull from the 1-year ACS for 2021 for Hawaii. So let's jump over there and try this out and see what we get. It's really pretty quick for a single state for the 1-year ACS. We just pulled down about 15,000 rows. And we get our data set here. We can print out our data set if we want to, or we can view it the way we've learned today. And let's talk through this a little bit, but I'm going to do that in the slides so you can see a little bit better. These are the columns that are returned by default, and we have an opinionated approach to working with PUMS data in Tidycensus that is inspired by the way that IPUMS does it, but I think is helpful. You'll notice we asked for age, household type, and sex, and we got a bunch of other columns back. And why did we get all those columns back? It's because we return in Tidycensus a number of columns by default. The serial number is one of those default columns. That's your household ID or your household serial number. So one of the amazing things about ACS microdata is it gives you people organized into households. So you can actually do like family level analyses and think about, okay, for people that have a graduate degree who live in this area at this age, like how many kids do they tend to have? It is super fascinating, the type of research and analytics that are enabled with PUMS data. And so you'll see here, these first 5 records, that is an actual household in Hawaii. Now it's all anonymized. So they use anonymization and swapping. So these aren't real people per se, but the structure itself is preserved as such that we can make reasonable and valid inferences about family and household structure, which is really cool. So we have here in this household in Hawaii, we have one person age 32. It looks like the sex is 2, so that's female. So we have a female age 32, a male age 31, and then 3 children. It looks like we have 2 boys age 12 and 9, and then we have a little girl age 2. And what's interesting about this is you see the SP order. That means basically the order within the household. If you're doing sort of household head type research, or if you want to limit to only do household level research, what you're going to want to do is a subset for where SP order is 1, and that'll allow you to get unique households. WGTP and PWGTP are critical columns to understand. WGTP is the household weight. So this is approximately how many households are represented by this household. And you'll notice that all records in the household have the same household weight. That means in a person level data set, you don't want to tabulate the household weight column because it's not going to make sense. But this household of 5, you can think about it this way. This household of 5 with this structure, 2 parents age 32 and 31, I guess we don't know for sure if they're parents because we would need to look at another variable, but they're the adults in the household. And then 3 kids age 12, 9, and 2 are roughly representative of approximately 134 households in this geography in Hawaii. The PWGTP, that's going to be your person weight. And so you can think of that as this person. So it's a woman in a family household, age 32, she represents approximately 133 other people, just like that with her characteristics in Hawaii. And so we use those weights to roll up our information to learn a little bit more and make these custom tabulations. So that's how you understand kind of the general structure of PUMS data in Tidycensus. Moving forward, I just talked about all this on this slide, so I'll keep moving that forward. The weights columns are essential, but what the weights columns do is, again, they allow us to take the individual level data and then make aggregate level inferences. And so I'm 39 years old. I am turning 40 next month. And so maybe I'm interested in analyzing 39-year-olds in Hawaii. What I can do is I can use that filter command like we just learned, and I could filter for all of those people in the sample that have an age of 39 and maybe ask the question, how many people are age 39 approximately in Hawaii? So let's take a look at that. One way that we can do that is we sum over the weight column. So in theory, the sum of the weights is going to reflect the overall value. So let's try this out. How many people are in Hawaii? How many people are age 39 in Hawaii? Let's try it. So according to this, there are about 1,441,553 people in Hawaii, of whom 17,381 are age 39 like me. Now, I live in Texas. I wish I lived in Hawaii, but I'm not one of those people. But that is the estimate that we get from our PUMS data. 2 things. Did we get the right answer? PUMS data are calibrated to population and household totals in ACS. And so larger tabulations, they should align with what you get in the published tables. And we can check our answer by using get ACS for the population of Hawaii. Let's take a look at it. I'm going to run get ACS. Geography is state. Variables is the variable for total population. I'll do state as Hawaii for the 1 year 2021 ACS. I run that and check this out. My sum over the person weights is identical to the published ACS estimate. I just checked my answer and I got the same answer, which means you can see how that calibration works. What about the number of people age 39? Well, I can't check my answer because that isn't found in the published tables. You can't get 1 year of age data, even the detailed tables. You can get 1 year of age data for some ages, but if you actually look at it, you can't go that granular. And so this is where the power of PUMS data really starts to come in. I can go in, I can look at stuff. Now, granted, it will be characterized by uncertainty. Are there actually 17,381 39-year-olds in Hawaii? No, there aren't. That is an estimate, and there's going to be some error around that. How do we calculate that error? I'm going to show you in just a moment. But because it's a smaller estimate, we're not talking total population here, there's going to be some uncertainty associated with that. So how do you start to build workflows with PUMS data? Well, for one, you got to figure out what your variables are. And we have a built-in data set of variables for the ACS PUMS. If you have an older version of Tidycensus on your computer, this won't work quite right. And in fact, the PUMS data itself might not work quite right with an older version of Tidycensus. So make sure that your Tidycensus is up to date, because I just updated it a few weeks ago for the 2021 5-year ACS. PUMS variables, which again, credit to my co-author, Matt Herman, he designed this whole thing. It gives you detailed information about all the variables in the PUMS, and you can go in and browse and figure out what everything means. So it's built into Tidycensus. So all you have to do is just do view PUMS variables. It's going to pop up and you can browse. And so it's separated by survey and year. And then you can look at the variable code. That's what you use to fetch data. Those names are more intuitive. And then we get an intuitive variable label, and it tells you all sorts of stuff about what the minimum and maximum values are, what the different data labels mean. So let's say I go to like sex. So the sex variable, I can see here that it's a person level variable. It should come through as a character or text. 1 means male and 2 means female. So the PUMS variables is super useful for designing your analysis on the one hand. It is also useful for another reason. We use this data set internally to allow you to do dynamic recoding of your variables. And by recoding, I don't mean replacing the existing values. It actually appends special recode columns to your data that show you what the different values mean. And so if I specify recode equals true, it's going to take the categorical or text columns and give me new columns that show what those categories mean. So let me show you that. I'm going to run this Hawaii PUMS recoded. Looks like I need to redo this. My session, I believe, reset. I'm going to run this through. And we're going to take a look at our recoded and check this out now. There is a state label. Everything's Hawaii. There's a household type label. All these households are group quarters or vacant. But if I go down a little bit further, some of them are married couple of households. Some of them are female-headed, are non-family female-headed households, non-family male-headed households. There's a ton of other stuff in here. And then we have a sex label as well that shows you what that label is. So we use PUMS variables internally to give you more informative data back, which is a feature I really like. PUMS data sets can get really big, especially from the 5-year ACS, because it's giving you information for all those 5 years. And so you can do dynamic filtering on the server side rather than on the R side, which is nice, and what that means is, in a little bit less technical language, is you can send a request to the Census API to give you back pre-filtered data. So let's say I want 5-year ACS data for Hawaii for the same variables, but I only want data for females aged between 30 and 49. So I'm doing like a specific demographic analysis. I specify as a list object the variables filter where sex should be 2, age, just give me back those ages between 30 and 39. And to show you how that works, I can run this. It doesn't take too long to run. I get back about 8,500 total observations, and you'll notice sex is always 2, and the ages are all between 30 and 49, just like I requested. And so, next thing, and I'm just looking at some of the questions. There's some really good questions in here that I hopefully will get to some of them. One of you, if you got that build longer spec error, you need to update Tidycensus. You have an old version of Tidycensus, and that's why it's not working. So do install.packages Tidycensus. All of this functionality needs the latest version 1.3.2 of Tidycensus, which is the latest published version of Tidycensus to work. So make sure you update that, and that should resolve that error. Moving forward, you might ask yourself, and this is a really common question, okay, it's great to be able to do analysis at the state level, but I want to do county level analysis. I want to know about Honolulu, or can I do neighborhoods in Honolulu and figure out how many 9-year-olds or 39-year-olds live in this neighborhood in Honolulu? It's trickier because, again, when we're working with data from the PUMs, there are strict confidentiality measures that are taken to preserve anonymity of survey respondents. And so, in this particular example, we're thinking about a situation here where you can't just get individual level records all the way down to like the neighborhood level. There's only one way to do that. And some of you, if you're Census Power users, you may know about it. I'm an approved researcher at something called a Federal Statistical Research Data Center. And frankly, it's really hard to get access to these data centers, really hard. It took me years to get access. And that's where you can get individual level microdata all the way down to, I want to say, the census block level, if I remember correctly. But that is, you have to be affiliated with an institution that pays a fee that allows you to go. You have to get special status with the Census Bureau. It's really hard to do that. And so for most of us, 99% of us, that's not going to be an option. But we still want to do geographical analysis. We want to know how, characteristics vary from one place to another. We can do that with something called PUMA, the Public Use Microdata Area. So PUMAs are the geography in PUMS data. They are areas that are redefined with every decennial census that tend to include between 100,000 and 200,000 people. So they might be a subset of a large county or collections of smaller counties. And they still allow us to do some reasonable geographical analysis with our PUMS data. Now, we're not covering mapping until next week, but I want to show you how PUMS works and how we get that information. And so I've already said some of the stuff on this slide, something that's important. The 2021 ACS uses the 2010 PUMAs. The 2022 ACS will use the brand new 2020 PUMAs that just came out a few months ago. So every decennial census, after the decennial census is done, there's a whole process that's done in concert with local officials to define PUMAs in ways that are intuitive and reflect local geographies. And so we're going to preview some of next week's spatial tools to show you how to look at PUMA geography in Hawaii. So if you run this bit of code, you're going to learn next week the Tigris package, which I wrote for working with census shapefiles. And you can learn the map view package, which I did not write, but I use daily to do interactive viewing of data of spatial data in R. And so PUMAs, if we run this bit of code, what we'll get So let me grab that real quick. Is an interactive map. It's going to pop up here. I'm going to have to put in Hawaii Puma map. And it's going to show me, I'm going to zoom in here to Oahu. All these shapes are pumas. So this is the most detailed level of geography you can get in the PUMS data. So I can identify records for these different slices of Oahu, because in Hawaii, most people live in Oahu. And so I could identify records that live in East Honolulu, that live in northern rural Oahu, that live in more urban Honolulu. I can do that. That's about the level of spatial granularity I can get. Outside of that, Maui County and Kauai County. So we've got here Maui, Molokai, Lanai, we've got Kauai as well. So Maui County and Kauai County are together in one Puma. And Kalau County, which is the little tiny county on Molokai. And then Hawaii County itself, the Big Island, is its own Puma. So there are geographical limitations, but you still can go below the state level. And so if you want to get data by Puma, put in the variable Puma, and it's going to give you that back. So let's go from the 5-year ACS. Let's take a look at age by Puma. And we can pull that in. We'll get it. So we've got about 10 minutes left. And in the last bit of time, I want to cover the topic of uncertainty in the PUMS. Because the tabulations we've been doing, as I said before, it's a smaller sample than the regular ACS. There's going to be uncertainty, but how do we calculate that? And this is an advanced topic. This is not something that's easy to do. And even the Census Bureau admits that this is hard. What we tried to do with Tidycensus is streamline this process for analysts. And I'm very happy with that implementation. And if you pick up a copy of my book, chapters 9 and 10 are all about PUMS data. So if you want a review on any of this stuff, please do pick up a copy and take a look. In PUMS data, the way you calculate standard errors from which margins of error derived is through a method called successive difference replication. Not going to get into the math behind that. You can read my book to learn more about it, or you can follow the link in the slides. But the idea is, in a nutshell, that the census provides something called replicate weights, and they provide 80 replicate weights for each individual record in the microdata. And replicate weights are alternative weights for those records to reflect uncertainty. So we have a published weight for a given person or for a given household. But then the replicate weights reflect all other possible weights that we could conceivably use. And those weights form a distribution that allows us in turn to calculate standard errors. And if you're thinking, well, wow, that sounds like there's some of you are very comfortable with this. Some of you, that sounds like a lot of math to get to where you need to go. This is why we built in some tools that I'm going to show you to accomplish this. So first and foremost, getting replicate weights is hard. They're pulling down 80 of them. So for one thing, the Census API limits you to 50 variables in a request at a time, and there are 80 replicate weights. So what Tidycensus does is it sends multiple requests to the API, and all you have to do is say rep weights equals person or rep weights equals housing, and it'll give you the appropriate replicate weights back. Let me show you how this works. I'm going to pull down my replicate weights from the 1-year ACS. You'll notice it makes 2 calls to the API. We print out 2 messages so you know what's happening under the hood. And if I open my replicate weights data set, look, it has 87 variables. So these are all of the people in the Hawaii microdata data set. They've got their person weights, and then they have a whole set of alternative person weights as well, 1 through 80. And check this out. Remember when we did some like Hawaii PUMS replicate, we'll just do this for purposes of illustration, and we summed over the person weight. And we got the actual population of Hawaii. Well, look at this. I could pick any other arbitrary person weight. Let's do person weight 5. And it also sums to the actual population of Hawaii. But if we look at this person weight and this person weight, this person is 65, but for person weight 5, it's 2. So it's reflecting uncertainty. This person could be 65 people, it could be 2 people. It could be 132 people. There's a whole range of possible people that it could be. And then when you tabulate up, you're generating a distribution of values that allows you to, again, start to characterize uncertainty around your estimates, which is extraordinarily helpful. That said, PUM survey samples are complex, and doing those actual calculations tends to require, a fair amount of reading and a fair amount of coding to get right. We've built in functionality to help you format that. And we've linked to the survey and surveyor package, which are R's infrastructure for handling complex survey samples, that tries to streamline this process. Because again, while it does take a certain level of technical ability traditionally to do these calculations, we felt that being able to do this is so important. Understanding uncertainty in your tabulations, that we want to expose some tools that allow for those calculations. The toSurvey function will format your data as a special survey data set in an appropriate way to allow for tabulation. And mindful of the time, I just want to show you a couple of these examples. The surveyor package then takes a survey data set, a complex survey sample, and then calculates appropriate survey weighted metrics, such as, let's say I want to do a tabulation of the uncertainty around the number of 39-year-olds in my data set. So I had estimated 17,381. Let's figure out a margin of error around that. So I'm going to run this here, and I'm going to talk through exactly kind of what's going on. I'm going to take my replicate weight data set, and I'm going to convert it using toSurvey to a complex survey sample, like a survey formatted data set. Here, let's read through this. I filter my data set for those rows where the age is 39. I use survey count to tabulate that. So I'm now doing survey weighting. And in doing that, I get, using surveyor by default, N here, and NSE, which is the standard error. The margin of error, you can convert a standard error to a margin of error using formulas that the Census Bureau recommends. For a 90% confidence level, we multiply our standard error by 1.645. And so my margin of error, my uncertainty around the number of 39-year-olds in Hawaii is they're about 17,381, plus or minus 2,776, and we're 90% sure that's true. So this is how we start to get that correspondence. The next step that I want to show you is you can actually do this within a group by and summarize paradigm, like we talked about before. Here, let's say I want to know the median age by Puma. So among these different Pumas, what is the median age by Puma? This is something that you can look up in the published tables, but I wanted to be able to check our answer. So I'm going to show you how that works. Here, I'm going to run this. To regenerate some of this stuff. And if you're seeing some of your objects disappearing a little bit, you might be hitting some memory issues in Posit Cloud. Posit Cloud is amazing, but again, if you're wanting to do some real work with this, you're either going to want to subscribe to a Posit Cloud account, or frankly, you're going to want to boot up your own version of RStudio. So let's take a look here. We've estimated a median age with a margin of error around that. Looks like the oldest Puma, the median age is 49, plus or minus about 2. That's Puma 303, which is going to be this East Honolulu Puma. It's one of the wealthier areas of Honolulu. The youngest one, which is 29, is going to be 301, and that's our rural Oahu Puma. So we get a sense, even within Oahu now, we can actually get a sense of some of these demographic differences. Let's go ahead and pull down some information using get ACS to check our answer and make some comparisons. I'm going to open this in the data viewer and we can look back and forth. So we're actually pretty close. It's not the same because our underlying sample used to tabulate this is different. And if you can get aggregate tables from get ACS, use that before get PUMS. But where PUMS data is fantastic is to get information that you can't get otherwise. But look how close we are. So this one here, Maui County, Maui, Kalao, and Kauai, 42.4 with a margin of error of 0.4. Yeah, we're right there. We calculate a margin of error of 0.4. The median, because we're using microdata, we're not going to have a decimal, but the values are pretty close within about a half a year. So there's so many things that you can do with this. I really appreciate you sticking around, even if you came for part of it or all of it. Over 200 of you stayed the whole time, which is, I'm just so appreciative of that you'd spend 3 hours learning about this stuff. Next week, please do consider signing up for next week's workshop, all about maps and spatial data. I'm really excited. So thanks again for your time.